Okay, so we have two basic laws for magnetism. They're pretty straightforward. One of them you know just by because you played with refrigerator magnets once in your life, right? So you know that magnets have the ability to repel each other, right? You take two magnets. Every kid's played with magnets, even if it's just on your refrigerator magnets, and you know that if you orient them in a certain way, you can get magnets to like push away from each other, right? And that's because north poles would repel a north pole. Okay, a south pole would repel another south pole, right? Like poles repel each other. It's kind of like, and it's almost like they're coming from the same phenomenon, almost, right? It's like electric charges. Opposite electric charges attract, like electric charges repel, right? And magnetic fields no differently. Okay, almost like that, right? Okay, so check this out. The Earth is really interesting because the Earth has a magnetic north and south pole. Have you ever used a compass? What direction does the North Pole needle of the compass point? North, right? That North Pole of your needle is the North Pole of that magnet on the needle. Okay? So if the North Pole of the magnet is attracted to the North Pole of our Earth, that means our Earth's North Pole is actually the South Pole. Okay, so the Earth has a north and south magnetic pole, but it is flip-flopped right now. Okay, the Earth's north magnetic pole is actually in the south pole of the Earth. Okay, the Earth's south magnetic pole is actually in the north pole. So when your magnet points north, it's pointing north, the direction we call north, but it's actually pointing at the south magnetic pole. Okay.
So eventually it's going to line back up to north, south to south.
Yeah.
Is that something that's going to happen gradually or just
Yes.
from day to night?
Gradually. It will not happen. It won't just flip. It'll happen. It takes.
Then even though the north and the south pole or north and south ends of the world are going to stay in the same position,
Yes.
right? These poles are just going to change little by little
Yes.
over time in a different part of the world until
Yes.
they line back up.
Yes. 100,000 years from now, our north and south pole is going to be in some weird random position.
So would those lights that happen at those ends just happen in different parts of the world because
Yeah.
the poles are moving?
Yes, exactly. Exactly.
That's cool.
Kind of neat, right? So yeah, the Earth's magnetic field flips every couple 100,000 years, and right now it's upside down, and it will gradually flip the other direction. Okay.
So is it moving little, obviously tiny bits every day,
Yeah.
not just like a whole giant section in one day?
No, it's
months.
it's precessing. It's slowly moving as the Earth's core is rotating in slightly different directions. Good. So the Earth's magnetic pole can and does change its direction. Did you know? I don't know if you know this, but the Earth's magnetic north. So the magnetic south pole that's up north, right? It's not in the position where true north is. Okay. So if you are if you're somebody who's trying to use a map to navigate, okay, when you use a map to navigate, you also usually use a compass, right? Your compass does not point to true north. Your map's going to be assuming true north, right? Your compass will point to magnetic north, or what is truly magnetic south. We just call it magnetic north. That's the direction the compass points. So your compass will point one direction, where true north is a different direction. Okay, and that changes the amount that those two things differ by is called declination. Okay, and that changes depending on where you're at, what longitude you're at on Earth. Okay, so people who want to learn to navigate have to learn where they're at on Earth, how much of this declination do we add into our compass, okay, to account for the difference in magnetic north and true north, okay? Last I checked, North America, right where we're at, is about 14 degrees of declination. That means to put it simply, that means there's a 14-degree difference between true north and magnetic north. So you have to counter your compass, you have to counteract what your compass is doing to account for that. So you have to and your cheap compasses don't do that. There is no adjustment for that. But nicer compasses, they'll often have like a rotating bezel and a bunch of fancy extra things. Those extra things on those nice expensive compasses are to do that. So you can use a map to navigate correctly. Your phones do that for you. If you use your phone to navigate, it's just using a compass and a map, okay? the phone's compass has to account for where you're at on Earth, right? And now it does use global positioning to help, right? But the map is built off that, and it has to consider that too. So but that's interesting, right? Magnetic north is not where true north is. It's not even, the same side of the planet, right? Magnetic north is actually down south. Okay, so that's really neat. Everything's flip-flopped right now. Give it a couple 100,000 years. I forget exactly where we're in. I think don't quote me on this, and people are listening to this on the YouTube, don't quote me on this. Don't get mad at me. But as far as I remember, I think we're something like 10,000 years into the current age of where the poles are. So we've got a long time before they're gonna be flip-flopped again. Yeah. And by the way, all of that comes from, like, do you guys know where our magnetic field comes from? Like, why do we have why does Earth have a magnetic field? Because it's not because Earth is spinning. You only get magnetic fields when electric charges spin. The core, right? The core is iron, right? Iron is ferromagnetic, and so that moving, swooshing iron core generates a very strong electric charge, generating a very strong magnetic field around Earth. Well, for our purposes, it's weak, but it's a big magnetic field, so it's strong. Okay, so, yeah, you guys ever seen the movie The Core? With oh god, who are the people in that movie? But anyways, great movie. A lot of good actors, right? Stanley Tucci's in that movie, fantastic actor. Anyways, but the core, right? The whole purpose of that movie is to go, what would happen if the Earth's core stopped spinning? Okay, just stopped, right? And it happened to have stopped because we screwed it up really bad by detonating some weapons, blah blah blah. Anyways, in that movie, the Earth's core just stops spinning, right? And who's seen that movie? Let me see. I know Michael's seen it. Okay. What happened in that movie? Like, what happened to Earth during that movie? Remember anything happening? Michael, remember anything happening weird? It was weird?
Like the animals couldn't navigate.
Yeah, that's great.
Compasses went weird.
Compasses wouldn't work. Animals couldn't navigate, right?
Computers stopped working.
Why couldn't the animals navigate? Like, how do birds know how to go to migrate north and south? They follow the magnetic field lines that Earth has. They don't know that they're doing it, but they follow the Earth's magnetic field lines. So do lots of animals. Okay, they use these magnetic field lines to navigate. And if the Earth stops spinning, the magnetic field stops. Okay. All of a sudden, during that movie, right, the atmosphere kind of breaks apart, right, and then the sun's rays kind of come through and start like melting and boiling the ocean. It's obnoxious movie. The Earth's rays come and start boiling the oceans, right? Well, what's happening? What they're trying to show you is that when the magnetic field stops, when the core if the core were to completely stop, the magnetic field would go away, and the magnetic field for our purpose on Earth protects us from the sun's rays, right? Earlier when we were talking about the northern and southern lights, we were saying that the sun's rays are the harmful parts of the sun's rays, the particles from the sun, are caught by the magnetic field and oriented into the north and south poles of the Earth, right? We're protected from the dangerous particles from the sun because of the Earth's magnetic field. And if that were gone, our atmosphere would be entirely wiped away, blown away. That's what happened to Mars. Okay, that's why Mars has almost no atmosphere, is because it lost, if it had a magnetic field ever, it lost it, okay? And it's why they think there was water and stuff on Mars and an atmosphere. They think there was a water, an atmosphere, all this stuff on Mars, and it was blown away because Mars lost its magnetic field. Okay, if that happens to Earth, we would lose our magnetic field and our atmosphere would be completely blown away, and we would have no protection from the outside world, space, right? Okay, so good. Remember, like poles repel, opposites attract. There's a law of magnetism called Gauss's law, and it's really not that hard to understand. The strength of a magnetic field is proportional to the product of the strengths of the two magnets. So let's start there, okay? You have two magnets. Take the strength of, don't even worry about how do we quantify strength right now. Just think about, you have two magnets. The force is proportional to the strength of those two magnets, okay? If the magnets are both strong, then the force is strong. If the magnets are both weak, then the force between them is weak, okay? The way to calculate it is to multiply. That's why they say the product of the pole strengths. So take whatever the strengths are at the poles, multiply those two strengths together. That's the strength of the magnetic field. Ignoring distance right now, okay? So proportional to the strength of the magnets, that's the thing to take away. We're not, this formula, Gauss's formula that you had to do in your homework, we're not going to play with that formula hardly at all, okay? We just need to know what it says, okay? That's something so important in learning the basics of physics, the basics of all of this is like, you're not a physicist, you are not an engineer, you're not going to have to sit down and calculate quantities, calculate magnetic field strength at certain distances with different magnets, right? All you're going to need to do here is tell me, what is this equation telling us? Okay, and it's telling us that magnetic fields are stronger when the two magnetic fields are stronger. Okay, that the product of the two magnetic fields are stronger when they're both strong, weaker when they're both weak. So you have two magnets, there's a force between them, okay? The force is given by the multiplying the two magnetic forces together, okay? And guess what? The force gets weaker the further apart the magnets are from each other, right? You've taken and played with magnets before, right? You know when you get them right up close to each other, they either pull together, right? Or they repel. And play with the repelling ones first, right? As you push the two north poles together, they begin to repel. You feel that repulsion, right? And you push harder, and they push back harder. And you push harder and get them closer, and they push back even harder. Eventually, if it's like a weak enough magnet, you can smush them together, right? But it takes a lot of energy for you to do that, right? The force gets stronger the closer they go together. Are the magnets getting stronger? No. The force is getting stronger because the distance is becoming smaller, okay? So, the force is inversely proportional to the square of the distance between the poles of the magnets. Again, don't worry too much about that. What I need you to take away here is that the force is inversely proportional to the distance. Okay? Simply put, as the distance increases, the force decreases. The force between them decreases. What law does this sound like? It even says it right here, sorry. The inverse square law, right? This is this is not unlike the inverse square law of electromagnetics, okay? Because it's all coming from the same phenomenon, right? Electromagnetism. Okay, so when you look at a formula like this, this is Gauss's formula. The formula says the force is equal to, ignore the K, multiply the forces together, and then divide by the distance squared. Okay, so if the distance is 1, then the force is just equal to the two multiplied together, the two forces multiplied together. All I need you to take away is the relationship here. Okay, force between magnets is proportional to the product of their strengths and inversely proportional to their distances, the square of the distance to be specific. Okay. So you had two magnets, they're 1 inch apart, okay? Whatever the force is between them at 1 inch apart, if you move them to 2 inches apart, which is doubling the distance, the force will now be 4 times weaker. That's the inverse square law, okay? And remember it simply, remember this. For every doubling of the distance, the inverse square law says the force drops by a factor of 4. Okay, every doubling of the distance cuts the force 4 times. Okay. So the units used for this, they'll give an example here in just a second, but the units used, Gauss, interestingly, the unit used for small magnets. So, refrigerator magnets, 1,000 Gauss. Good. I want to say something here, but I'm wondering if I should refrain. Just all I want to say here is that remember that all the units we're using, right, are what are called derived units. These are derived from more basic quantities. So the Gauss has the Gauss unit is built on other units of measure, okay? We're not going to worry too much about that right now. That's something for physics. I just want to remind you, those of you who've been through physics know that there are like fundamental units of measure, right? Time, distance, and I don't know, the mass or whatever. But the point is that there are fundamental units, right? And every unit we use that we talk about in everything are all derived from those fundamental units. So the Gauss has something that it's built on. Don't worry about that right now. Yeah, so for reference, fridge magnet, 1,000 Gauss. Earth's magnetic field, 1 Gauss at the poles and a half Gauss at the equator. Are we at the pole of the Earth? Are we at the equator? No, which were we closer to? I think we're closer to the equator, right? So we are closer to a half Gauss in strength than 1 Gauss. But the point is that there is a measure of Earth's magnetic field, and it is much weaker than a refrigerator magnet. If it were as strong as a refrigerator magnet, then we'd be having lots and lots of problems, right? All magnets would be, all like large macroscopic things would be attracted to Earth's magnetic field, and so all your refrigerator magnets would go flying towards Earth's magnetic field, and they would be all trapped up in the outer atmosphere, and that wouldn't be a good thing for us. It'd be like someone turned on the MRI machine for like all of Earth, right? MRI machines operate at much higher values, shown here. So the value used for big magnets is just a big unit, okay? We call it the Tesla. Tesla for Nikola Tesla, not for Elon Musk and his company Tesla, although that's the name that Tesla gets attached to nowadays. Nikola Tesla was the inventor of the AC motor. At least he invented the one that worked. And he's famous for having done that and worked with Thomas Edison to develop lots of important things. So every time your window rolls up and down, that's because of Nikola Tesla, okay? Every time you start your car, that's because of Nikola Tesla. Every time you turn on your hair dryer, that's because of Nikola Tesla. And every time you turn on your washing machine or dryer at home, anything that has an electric motor in it, that's because of Nikola Tesla. So he basically gave you your entire modern world, and most people don't even know who he is, right? He's a cool guy, really interesting guy. I can tell you more about Tesla if you ever want to know more. But anyways, the unit Tesla, abbreviated capital T, is used for big magnets. And so to give you a reference, 1 Tesla is roughly 10,000, not roughly, it is exactly 10,000 Gauss. So 10 refrigerator magnets all together is 1 Tesla in strength, technically, roughly speaking, right? If a refrigerator magnet is 1,000 Gauss and a Tesla is 10,000 Gauss, then 10 refrigerator magnets worth of magnetic strength. MRI machines operate around 1 Tesla, although I have seen some listed as having 2 Tesla. MRI machines use magnets to orient your magnetic domains in your body. Remember, you are built on atoms, right? Your atoms can be magnetic dipoles, and so we can orient those atoms in a certain way. So what they'll do is they'll put you in this magnetic field, so all your atoms get pointed in one direction, and then it's just sort of complicated and interesting, but then they basically run radio waves through your body, and then they measure how those radio waves are exiting your body, and they can build images from that. Okay, kind of complicated, but what's really nice about MRI is that it gives patients no radiation exposure. So even though it's part of radiology, no radiation is given to patients. Okay.